This is the 26th lecture of this course. Recall from the last lecture that we investigated the following, that suppose I have two finite dimensional vector spaces V and W and another finite dimensional vector space U. Suppose the dimension of V is n, dimension of W is m, dimension of U is L, and T is a linear map from V to W, and this is a linear from W to U. It is an ordered basis B B prime and B double prime. Then the matrix representation of the composition B B prime. So, the matrix representation corresponds to composition of linear, the corresponding composition of linear maps, and corollary. One corollary we have already seen. If m equal to n, then T inverse B B prime is same as B prime B, T B B prime inverse if T is so if T is invertible. Okay. Then okay. So, we have thus proved that this one happens. Next we will if you remember that we are in the last lecture we said that we are currently dealing with two questions. One question is likewise sum of matrices corresponding to the sum of linear transformations. So, likewise whether matrix multiplications corresponds to some operations of linear transformations or not. That is what we have answered here, and now we will consider the second question. What was the second question? Second question, suppose we have B and B prime, where these are the ordered basis of B and W. Suppose we take some another ordered basis, let us say B1 and then B1 prime. So, with respect to B and B prime, the matrix of T is this, and with respect to the B1 and B1 prime, the matrix representation of this is this. So, the question is, what is the relation between these two matrices? Okay. We will see that we can answer that very easily from this relation. So, what we will do is the following, that from V to V, V to W, and from W to W. So, here we will take the identity map of V, here I will take the identity map on W, here I will take these as usual. So, this is I need to get this. So, B1, B, B prime, B1 prime. So, these are my choices of ordered basis. So, it is now very easy to see that this entire composition, that IW compose T compose IV with respect to B1 and B1 double prime. What is that? So, if you first take the composition of this 2, then so what is this composition? IW T IV. So, from the usual rule of from the definition of compositions, identity maps, they do not change at all. So, this is T, this object is nothing but the matrix of T with respect to B1 and B1 prime. I repeat, if I consider the identity matrix here, identity transformation here, and look at the matrix representation of this composition with respect to these ordered bases, then I get this one. Okay. Now, we know that from this relation that the composition of the matrices is that corresponds to I mean the composition of linear maps, their matrix representation becomes the multiplication of the corresponding matrices. So, let us do that. So, T compose IW. So, the matrix, so this is B and B1 prime here together with identity, with B1 and B, right. I think I have sorry, this will be reversed. IWT, okay, because the whole composition can be regarded the composition of this, and then with that we compose this. Now this is nothing but T itself, okay. Now what can we say here? So, well, it's better to keep it in the other form, IW compose T, because that further helps me to so this will be TBB prime and then IW TB, so TBB prime, B prime, B double prime, and with that I have IV B B IV, sorry, B1 B. I think I have somewhere missed B prime, B prime, I think B1 prime, not B, nothing B double prime, B1 prime, yeah. Then now that looks fine, now that looks fine. So, we see that this matrix is, I mean this matrix, so the relation between these two matrices is, this matrix is nothing but multiplying this that matrix by two other matrices, and let's see what these matrices are. So, this is the matrix of the identity map with respect to B1 and B. So, what does that mean? So, it means that, so what, let us go slow one by one. So, the identity map. So, here we drop the drop V, B1 and V. So, what is this? What are we doing? We are doing, what we are doing is we are writing each and every basis vector of B1. So, this is, so I mean each and every vector. So, if try to understand, so what is the map here? Each V is getting mapped to V. So, the matrix of this linear map with respect to this and that, how do I get the matrix? So, what we are doing is we are taking every basis vector of V1 and writing that as a combination of the basis vectors in V. So, I mean earlier we have B and now we have B1, okay. Earlier I repeat, earlier we had B, now we have B1. So, what we are doing is we are writing the, so earlier we are writing the new basis vectors with respect to the older basis, the basis new vector, we are writing the vectors in the new basis with respect to the older basis, right. Yeah, we are talking about this part. So, we had, please try to understand, we had B and we have changed the basis B1. So, every vector in B1 can be written as a linear combination of B, and those linear combinations, from those linear combinations we put the scalars along the column, and thus that gives me this matrix. So, therefore, the rightmost matrix here, that tells me that the rightmost matrix here, that is nothing but obtained by writing the new basis vector in terms of the, if we loosely speak the coordinates of a vector by some address. So, what is happening is, so what we are writing here, we are writing in this new coordinate system, the coordinates of the address of each of the vector of the new system according to the older system. And similarly, what we are doing here is we are doing the same, that is here we had IW B1 and IW, So, I of B and B1, B prime and B1 prime. So, earlier we had B1 B prime and here we have B1 prime. So, here we are doing in the opposite way, that is we are writing a old basis vector in we are writing the coordinates of the old basis vectors in terms of new basis vectors. So, here we were writing the addresses of the new vectors with respect to the old system, and here we are doing the opposite one, writing the addresses of the old vectors basis vector with respect to the new system, and once we multiply that is how we get this. Okay. So, that shows me that if we change the basis, then how these matrices are obtained. Okay. And one thing is worth observing, that is what is worth observing, that both these matrices are actually invertible matrices, right, because they are the matrix representation of some invertible linear transformation, this identity. So, there yeah. Therefore, if you can, you should write like this: B1 prime, B1 prime, B prime inverse, right. If we if we consider the inverse of IW, so it will be a map, and write the matrix of IW with respect with the, this is the first basis vector, this is the first in the odd set of ordered basis, this is the first ordered basis in the second ordered basis, then the matrix is nothing but the inverse of that. B prime B1 prime, yeah, T B and B prime I V prime. Do not get scared by the notation. So, try to understand, when we write this notation, you can simply think that this basis and this basis gets getting cancelled. So, therefore, the matrix is this and that. Okay, the same thing is being happened here. So, this cancels this, and just a minute, did I make any mistake somewhere? Yeah. So, when this cancels that, then this one will cancel this one. I think. Okay. So, I V with respect to, yeah, here we have B1, I V is B1, this is B, yes, I made now it is fine. So, ultimately we we need B1 and B1 prime. So, yeah, so this will cancel this will cancel this, and so we get this. Now, that is fine. Okay. And this matrix, the matrix with respect to the matrix of identity matrix of identity map with respect to B prime and B1 prime, that is nothing but the inverse of the matrix with of the same identity transformation with respect to B1 prime and B prime. Okay. Because once you if you multiply them, then you get the identity matrix, which we have observed earlier. Okay. So, we have already answered our question. Now, the advantage of writing this in this form, the same thing in this form, is the following, that gives us something very interesting. So, if in particular we assume that W is V, okay, and B prime equal to B, in particular, and B1 equal to B1 prime, then specializing this to this case, what we get is so matrix with respect to B, we get so B1 equal to B1 here, just a minute, yeah, B1 equal to B1 prime. So, that is same as TB identity map where what are we doing? Did I make any mistake here? It does not seem so. BB. So, this will come. So, again I will have identity map here. So, what is the map here? Let us see. So, this is the inverse of B1 prime equal to B1. So, B1 inverse, right. Sorry, B1 B inverse, B1 B inverse, and here what we have, let me just check for a while to make sure I have not messed up here in the notation. So, B1 prime, that is this relation. First we take the matrix of the leftmost one, namely here IV B1 B, and then this B1 prime. Then we when we break it here, we first again take this B prime and then B prime B1 prime. That is what we are having here. So, yeah, therefore, the here and in this case B prime equal to B and B1 equal to B1 prime. So, B1 therefore, identity just a minute, I think I made the mistake here. So, T B B prime, yeah. So, it will be just yeah, B1 B, yeah, now it is fine, B1 B. So, this is B1 B, okay. So, yeah, now you see that. So, this matrix alone, what is this matrix? B1 B, if you call it P. So, then this matrix is nothing but the inverse of that. So, therefore, we have in the form P inverse BB P, right, where P is that invertible matrix. Remember how this matrix is formed? So, earlier this was B was my basis and now B1 is my basis. So, every vector in B1 I will write that. So, in this new so I will write down the coordinates of this new basis, ordered basis, with respect to the earlier ordered basis. Okay. So, from the column of P I will simply, I mean by reading the columns of P. So, looking at the ith column of P, I know that what is going to be the ith vector in this B1, right. So, if this is my let us say alpha 1 up to alpha n, I know that and ith vector in B1 is going to be alpha 1 V1 plus 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 alpha n Vn, right. Okay. So, what we see is if we are, well, if the both V and W's are same, then the linear map from V to V, we usually call it a linear operator, and for linear operators it is rather interesting to I mean we will see why. So, I mean it is in a sense more interesting, well should I say interesting? Well, so for linear maps, for the time being let us just put this in this way. For linear map we often look at its representation with respect to a single ordered basis, namely B. Now, if you change for example for Fn to Fn, we in the examples we just took usual standard basis as the ordered basis. So, in that case we will use the following notation. We will not write B twice, we will simply write B once. So, therefore, after simplifying that notation we can simply see this, okay. We simply see this, fine. So, for a linear operator, if we change the basis, then the matrices are connected like this by we choose some invertible matrix P and then multiply from P inverse and from the left and by P from the right. So, what do I say if two matrices are related like this? We have already known the terminology. We know the terminology that if two matrices, let us say square matrices, are like this, where P is an invertible matrix, then we call A and B are similar matrices. Okay. So, what we have got is, if we change the basis of a linear operator ordered basis, I repeat, here we are considering the matrix, I mean very often we will do, and now we are doing consider the matrix representation with respect to a single ordered basis. So, if we change that ordered basis, the matrix that we are going to get becomes a similar matrix. Okay. What about vice versa? If we are given a invertible matrix, then from if we are given an invertible matrix, can we like given T B and now an invertible matrix, can we find a basis B prime such that with respect to B prime the matrix of T is going to be this. So, the question is regarding the converse. If somebody has given me some invertible matrix, can I produce a basis B prime? Actually, that is very easy to see. I have told you how to do that. So, given an invertible matrix, so from its ith column you call this, let us say Vi prime, this vector. So, now you prove that Vi primes, in fact maybe we have already done that if I forget. So, this Vi prime, that is also is going to form a basis of V, and with respect to this basis, if you call this B1, with respect to this B1, the matrix will be nothing but this. Okay. Because once you construct this B1, then I think here I have made some mistake. So, yeah, so here I must have written, yeah. So, otherwise I with respect to the single ordered basis B will be identity. Yeah. So, once we construct B1 like this, then I B1 will be precisely this P. So, thus what we see here is, one thing is very clear, that change in the level of base, they do correspond to an invertible matrix. That is, if I have two ordered base, so from one ordered base to another ordered base, how do we arrive? By means of an invertible matrix, okay, and vice versa as well. So, therefore, the matrix, all the matrices which are similar to TB are actually the matrices all the matrices which are similar to TB are actually the matrix representations of the same linear map T with respect to some suitable ordered basis. Okay. So, thus what we have got is similar matrices are nothing but the matrix representations of the same linear operators with different ordered bases. Okay. Now, from that we have an immediate corollary. What is the corollary? That if you remember, so what is the rank of a matrix, the rank of a linear transformation, namely the dimension of the image. Okay. So, we have seen that if we start with a matrix, let us say square matrix, or let us say not necessarily a square matrix. So, then the matrix gives rise to a linear map, and the rank of the linear map is same as the rank of the matrix, okay, because the image of the linear map is nothing but the column space of the matrix. So, concentrating on the on a square matrix. So, this square matrix we can realize it as a linear transformation from Fn to Fn. Okay. So, then any matrix which is similar to this A can be regarded as the matrix representation of the same linear operator with respect to suitably chosen, possibly different, or possibly different ordered basis of Fn. Okay. So, any matrix B, if B is PAP inverse, then P is nothing but, then B is nothing but the matrix representation of the same linear map with respect to, well, if it is better to conveniently put this in P inverse AP, because from that I can immediately read the new basis, namely given by the columns. So, if B is of this form, then I look at the columns of P and the columns are going to tell me what is the new basis, okay, because that is what we have seen from here. Oh, all right. So, what is the lesson? The lesson is the B is nothing but the matrix representation of the same linear map, and rank is the intrinsic property of the linear map. Okay. So, there is no reason that if we represent the matrix of the linear map with respect to some with respect to a basis, rank will depend upon that. Well, try to understand once again. Try to understand that in the general context, suppose I have T, let this be Fn, let this be Fm, by choosing ordered basis and passing through a coordinate system. Okay. So, remember, so if you call this, so this map is given, so this map is basically TBB prime x. So, these two are isomorphic, okay. Then you see the, I mean, image of T and this image of this map, that is the column space of T, column space of this matrix. So, column space of, they are isomorphic, right, by phi b prime, because it goes here. So, by isomorphism where it comes down, that is same as where it goes, that is very easy to see, right, because these are isomorphisms. What I am saying is the image of this map is, so well, let me put it in this way, phi b prime is an isomorphism, this means isomorphism from the column space of this. That is obvious, because these are isomorphism, therefore, dimension of the rank. So, the image of this linear map is same as image of its matrix. Okay. So, rank of T is same as rank of the right. That is very easy to see, because if somebody is in the image, then you drop it by phi prime, then that lies in the image of this, because that is how, I mean, whole things are made. So, what we see is given a matrix T, then for any B and ordered basis, given a linear map T, give for any choice of ordered basis B and B prime, the rank of T is same as the rank of this matrix. So, therefore, whatever B and B prime we choose, the rank of the matrix does not change. Now, you apply that to here, right. So, what do you get? The rank of B is nothing but the rank of, I mean, the rank of B is nothing but rank of A. Okay. So, therefore, with the immediate corollary is, without getting into anything else, similar matrices have same rank. Have same rank. Okay. All right. So, summarizing what we have seen so far. So, from this product formula of matrices, we have seen that if we change the ordered basis, then the matrices do change in this way, namely specializing that there is particular context, we get that by changing ordered basis we get similar matrices, we get matrices similar to this and vice versa, and following that as a corollary we find that all similar matrices always have the same rank. All right. So, we know that thus we are much more, we are comfortable with how to deal with matrix, how to deal with the matrices of we know how to deal with the matrices of linear transformation. So, and we know that suppose we have got the matrix that was some ordered basis, then how to get the matrix when we change the ordered basis, namely in general context this will be this, or in the very particular context which we will be dealing most often in the context of linear operators and with the single ordered basis, then we will see we will be always dealing with similar matrices. Okay. So, enough of this, let us now move ahead. So, okay. So, come back to where we are in the beginning of last lecture, or yeah, in the beginning of this lecture. So, for two finite dimensional vector spaces V and W, LVW from LVW to M cross NF, we have M cross NF, we have this. So, fixing two ordered bases B and B prime. Okay. We are there, and then this is a linear isomorphism. This we have already seen. Just to make a remark that if V W is V, then L V V. So, we will get square matrices. Then this linear isomorphism, well, for as I say, let us take for yeah, let us from, so the maps are always from V to V. So, well, we fix the basis V throughout, try to see what is going on. So, this is the ordered basis of V. So, so L V is nothing but the set of all linear operators on V. So, this map, I mean in general this map is isomorphism. So, specializing that to this case, it also gives you an isomorphism, but now it gives you something else. So, this also, I mean from all what we have seen earlier, I mean I should have mentioned earlier, but now let me just mention it, that in specializing to this case, this map preserves the product. I mean I will just put it as a remark, why I am calling it product, that you will understand, that you will be explained later. So, try to understand on LV, on LV by a product I mean composition. Okay. So, I mean we will call the composition here as the product. So, now what I mean is, if you take the product here and then send it by this isomorphism, that is same as you take the send the isomorphism then take the product. So, that is the meaning of calling it, it preserves the product. I should have mentioned that earlier, but yeah. Now, let us get back to this. So, LVW is the set of vector space of all linear maps from V to W. Now, specialize this when W equal to F, okay. The set of all linear maps from V to F. So, the set of all linear maps from V to F is usually, we denote this by, is called the dual of V, is called the dual of V, is called the dual of V, okay, and we denote it by V star, okay. Yeah, so it is denoted by V star, the dual of V, fine. So, so therefore, now specializing this general isomorphism in the which happens in generality to this case of dual, what we get is V star is isomorphic to, so what is M? So what was M? M was the dimension of W. So here M is 1. So M 1 cross N F. So these are all row matrices, right? So a row matrix, we we have already agreed that according to our convenience we will interchangeably write a tuple by a row matrix or a column matrix, right, that we have already agreed, depending upon our situation, that I will given a pair, given an ordered tuple, sometimes I will immediately convert it to the corresponding row matrix, column matrix, or sometimes row matrix. Okay, because whenever you have a row matrix or a column matrix, you can immediately get the tuple, and from a tuple we can get it. So interchangeably we will interpret a tuple as a row matrix or a column matrix according to our convenience. So that means here we will interchange, we will denote this by instead by Fn. Not denote, we will consider Fn in place of M1 1 cross Nf. Okay, identifying each and every row matrix by with the corresponding n tuple, and M1 cross Nf and Fn, they are, you see they are very naturally isomorphic. A row matrix is being sent to that tuple, and so therefore at the level of vector space nothing is happening. We simply write Vfn, Vn. So therefore in this very particular situation, we would like to see what this map is. So given a T, so what is TBB? So when W is F, so B prime, for B prime we just take singleton 1. Okay. So the content, what is this here? So we have already seen this. So if our B is V1, V2, Vn, then what is what was my T B? It was basically, so how to get this? So TV1. So then what will be the first component? TV1. This will be a real number, right? This way, sorry, membered in F. Similarly, TVN, in the matrix rotation, this is what will be my matrix. But now as I said that we will rather view it as the tuple. Therefore, the corresponding tuple is this. Okay. So in this context, when W is F, so we get this is a linear isomorphism. Okay. So try to understand that what we have got is very interesting. We have got is V, since the dimension of V is so both V is dimension of V is n, is isomorphic to Fn. Then so as a corollary to do we really need that? Maybe not. Well, just a remark I can put it here, that V star is isomorphic to Fn is isomorphic to V, because V has dimension n. So therefore, for finite dimensional vector spaces, V is isomorphic to its dual. So the noteworthy point is this you do not have a very natural isomorphism, in the sense that that isomorphism indeed depends upon the choice of the basis B. So you fix a basis B, then with respect to the basis you get, and with respect to the basis you get a isomorphism from between these two, and again with respect to the same basis you get an isomorphism, for that same basis you get an isomorphism from here to here, and then by composing you get isomorphism from V to V star. So it shows that they are the isomorphism depends upon the choice of the ordered basis. Now, let us come here. So, try to understand. So, this is a linear isomorphism. So, in the general context we obtained. So, we have a very natural, I mean in the generality we have seen that we have a very natural basis here, their pullback is going to be a basis here. So, in this very particular context what is going to happen, what is the natural basis here, E1, E2, En, right, is the ordered basis here. So, what is going to be its pullback there? So, what is going to be Fn, yeah. So, what is going to be its pullback there? So, what is E1? E1 is this tuple, right. So, the if we say T1, so what the T1 is the map which sends, if you remember how we arrived, how we found out the pullback of the elementary matrices, okay. Yeah. So, how do we do that? Yeah. So, T1 is going to be the following map which sends V1 to 1, and so T1 is the map, T1 will be sending V1 to 1 and T1 on other Vj's is 0. So, let me, so therefore, let me write the general formula for Ti. Ti is going to be the linear map that Tix, so Ti of Vj is delta Ij, where yeah, delta is delta Ij. So, it is 1 if I is j, right, 0 otherwise. So, in a sense T1 Ti, so using the notation Ti Vj is delta Ij, okay. Or more generally, what is Ti? Ti, I mean what is Ti of x, Ti of a general vector V, we should. So, if we decompose, if we write V in terms of the general, in terms of the V in terms of the linear combination of V1 V2 Vn, then what we see is xi Ti Vi, right, because x1 Ti V1 will be 0 unless I equal to 1, only ith term will survive. So, once it survives it becomes 1, this will be xi. So, therefore, what is, so therefore, Ti is the map which sends, I mean which sends each vector to its ith coordinate with respect to the ordered basis, right. So, therefore, Ti is nothing but the map, the projection to the ith coordinate, that map, right. So, yeah, we define there is a Ti is the so Ti and Vj, how is that defined, try to understand. I mean Ti Vj will be 1 if I equal to j, or 0 otherwise, and from that it shows Ti is the projection map, yeah, projection map onto the ith coordinate with respect to B. Okay. Well, let me introduce a linear term. So, earlier as I said, if V equal to W, then I will for on the context in the context when V equal to W, we will call the linear transformations as the linear operators. When W equal to F, then in that case I will call them a linear form. So, by a linear form on V or linear functional, I should rather, okay, functional. By linear functional on V, I mean a linear transformation from V to F. So, V dual is the set of all linear functionals, okay. And what are what are the examples of linear functionals. So, let me, so maybe I should have said that, then we will come back to this. So, for example, fix an I, so Fn to F, this we have already seen, sending this to Fi, okay. That is a linear functional which we called as a projection onto the ith coordinate, and I mean and we can generalize that to any finite dimensional vector space V. So, if V is let us say V has dimension n, then choosing an ordered basis B, we can send each V to its corresponding ith coordinate, where so V is xi Vi xn Vn, okay. So, this is what we have called here at the projection. So, this is the linear form which is the projection onto the ith coordinate with respect to V. Remember, in case of Fn, as I always say, we have a very natural choice of standard basis, but for general V we do not have a natural choice. There we have to put a ordered basis first, and for each ordered basis we will have for each ordered basis we will have a collection of TIs, okay. Each ordered basis will lead me to n such projection maps with respect to the ordered basis. Now, the main point is, if you come here, we have seen that this TIs because TIs are the pullbacks of EIs with as the dual basis of V. Okay. So, with that, so this is the definition of, so given an ordered basis here, we arrive at another basis of V star, which we are going to call as the dual basis. So, in the next lecture I will talk about that dual basis more. So, with that I will finish this lecture. Thank you.